A pleasant day, Ma'am Sarah Miserada, and good day, classmates. This is the group discussion of Group 2 with the main topic, organic compounds. This discussion primarily aims to describe the geometry of simple compounds, determine the polarity of simple molecules, describe the different functional groups, describe structural isomerism, and finally, describe the formation and structure of polymers. The presenters for today's video are yours truly, Andrea May Gilicop,
and Justin Joyliza,
Jade Russell,
Luxie Buncha,
and Ashley Marie M. Mortesa. This video consists the following topics, namely, organic compounds, geometry of simple compounds, polarity of simple molecules, different functional groups, structural isomerism, and formation and structure of polymers. At the end of this video, the glossary and the references used will also be presented. That would be all, and enjoy watching our video. Hello everyone, my name is Ashley Marie M. Mortesa, and today I am going to talk about organic compounds. First, let us talk about why is it called organic compounds. Do you know why? Well, it's not that complicated. These are called organic compounds because they are associated with living organisms. So now, how will you define organic compounds? According to Brightstorm, organic compounds are compounds composed of carbon, hydrogen, and often oxygen or nitrogen. So now that we know the definition of organic compounds, we will jump into their characteristics. According to the source I found, there are general characteristics of organic compounds. Number 1, organic compounds can be isolated as well as prepared in laboratory. Number 2, organic compounds comprise almost 90% of all known compounds. Number 3, organic compounds are mostly made up of 3 elements: carbon, hydrogen, and oxygen. Other elements like halogen, nitrogen, and phosphorus are also present but in a lesser extent. Number 4, organic compounds possess complex structures and high molecular weights. Number 5, their properties are decided by a certain active atom or group of atoms known as functional group. Number 6 is that organic compounds are mostly insoluble in water but soluble in organic solvents. So now we are going to talk about the types of organic compounds. So there are 4 important types of organic compounds: the carbohydrates, lipids, nucleic acids, and proteins. The 4 types or classes of organic compounds are found in all living things. Starting off with carbohydrates. Carbohydrates are organic compounds that are made up of elements carbon, hydrogen, and oxygen. These are the largest class of organic compounds found in organism. Some examples are glucose, fructose, sucrose, chitin, and cellulose. Next, we have lipids. Compared to carbohydrates, lipids have higher rate of hydrogen to oxygen ratio found. Lipids are used for energy storage, building structures, and serve as a signal molecules to help cells communicate with each other. Lipids has 3 major groups: the triglycerides, which are fats, oils, and waxes, steroids, and phospholipids. Some examples of lipids are cholesterol, paraffin, olive oil, margarine, cortisol, estrogen, and phospholipid bilayer, which forms the cell membrane. Next is nucleic acids. Nucleic acids are made up of nitrogenous base, sugar, and phosphate group. Cells use nucleic acid to code the genetic info of an organism. Lastly, we have proteins. Proteins consist of chains of amino called peptides. These serve many functions in cells. They are used to build structures, catalyze biochemical reactions, package and transport materials, and protein also help replicate genetic material. Some examples are enzymes, collagen, keratin, albumin, hemoglobin, myoglobin, and fibrin. Now, let us talk about the classification of organic compounds. There are 3 main groups of organic compounds depending on the nature of the carbon chains, namely aliphatic compounds, carbocyclic compounds, and heterocyclic compounds. Now, let us take a closer look with these 3 main groups. First, we have aliphatic compounds. Aliphatic compounds are organic compounds that process an open chain carbon atom. The name aliphatic comes from a Greek word aliphatos, which means fat. Aliphatic compounds are one of the major structural groups of organic molecules. These include alkanes, alkanesa, and alkynes. Next is we have carbocyclic compounds. This is when a large number of organic compounds possess rings consisting of carbon atoms only. Carbocyclic compounds are also classified into three categories. First, we have alicyclic compounds. Alicyclic compounds behaves like aliphatic compounds. The common examples of alicyclic compounds are cycloalkanes, cycloalkenes, and cycloalkynes. The second category is aromatic compounds. Aromatic compounds are organic compounds that possess benzene rings with characteristic smell. Some common examples of aromatic compounds are benzene, toluene, ethylbenzene, toluene, ethylbenzene, chlorobenzene, phenol, and etc. The last category for carbocyclic compounds is the non-benzenoid aromatic compounds. This is a class of organic compounds that does not contain any benzenoid ring but have an aromatic character. That would be the three categories of carbocyclic compounds. Now, let us talk about the last classification of organic compounds, which is the heterocyclic compounds. Heterocyclic compounds is the class of organic compounds that contain a ring with a carbon and other elements, commonly oxygen, nitrogen, or sulfur. Heterocyclic organic compounds have 5 or 6 heterocyclic rings which are stable. It contains conjugated double bonds, and the rings exhibit aromatic character. Some examples are furan, thiopene, pyrrole, and pyridine. And that ends the classification of organic compounds. After knowing the definition, the types, the characteristics, and the classifications of organic compounds, we will now end this discussion with knowing what is the importance of organic compounds in our lives. I have here 3 importance of organic compounds. Number 1, organic compounds are important because all living things contain carbon. Number 2, carbohydrates, proteins, and fats, and the basic structures of life are all organic compounds. Number 3, they are the basic components of many. For example, the carbon cycle that includes the exchange of carbon between plants and animals during photosynthesis and cellular respiration. Lastly, organic compounds are combined with metals, which forms organometallic compounds. These compounds are important industrially. They are used as catalysts, promoters, analyzers, as well as stabilizers. And that concludes my discussion about organic compounds. Thank you so much for listening, and I hope that you have learned something from me.
Thank you, Mr. Teza. When we talk about molecular geometry, it refers to the arrangement of atoms in a molecule. We can figure out what the shape of a molecule is by familiarizing ourselves with the Lewis and dot structure, as well as a couple of other methods and models that will be explained later on in this video. But for now, let's focus on the diagram at hand. The Lewis electron dot structure uses dots to represent the number of valence electrons that an atom has. The arrangement of the dots does not have any specific order and can be placed at the top, left, right, or bottom of the symbol, with no more than 2 dots on each side. The next step would be to apply the VSEPR theory in order to determine the molecular geometry of an atom. Now, what is the VSEPR theory? Well, it stands for valence, shell, electron, pair, repulsion. It displays the 3-dimensional structure of a molecule by focusing on the bonding and non-bonding valence electrons that are present within it. According to it, valence electrons will generate a negative electric charge that will cause each electron to stay far apart from each other as much as possible. It also describes the 5 main shapes of a molecule, that being linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral geometry. Molecules that have linear geometry have their atoms connected in a straight line, with bonding angles of 180 degrees. Examples of these are carbon dioxide. Molecules that exhibit trigonal planar geometry have a triangular shape and have bond angles of 120 degrees. Examples include boron trifluoride. Molecules that exhibit tetrahedral molecular geometry have 4 bonds on one central atom, with bond angles of 109.5 degrees. Examples include methane. Molecules that have a trigonal bipyramidal molecular geometry has a central atom with 5 bonds. 3 of the atoms are on the same plane with bond angles of 120 degrees, while the other 2 are on the opposite ends of the molecule. Examples include phosphorus pentachloride. Molecules that display an octahedral molecular geometry have 6 atoms on one central atom, with all bond angles being 90 degrees. Examples include sulfur hexafluoride.
The Axe method is another way of looking at molecular geometries, with A representing the central atom, X representing the number of sigma bonds between the central and outside atoms, and E representing the number of lone electron pairs surrounding the central atom. The steric number is known as the sum of X and E. It is associated by the total number of hybridized orbitals used by the valence bond theory. The VSEPR uses the steric number and the distribution of X's and E's to predict the molecular geometric shape. We can count the number of electron domains and use that many atomic orbitals to describe the hybridization of the central atom in a molecule. If you take a look at the carbon dioxide atom, for example, we can see that it has 2 electron domains. In order to participate in these bonds, the carbon atom takes an s orbital and a p orbital and hybridizes them, forming an sp hybridized molecular orbitals. For each energy level, there is 1 s, 3 p's, and 5 p's. In the case of carbon dioxide atom, only 1 s and 1 p is needed for 2 electron domains, making it sp hybridized. Anything that is sp hybridized will have a linear electron domain geometry. Another example would be BF3. In this case, boron has 3 bonds. This means that there are 3 electron domains surrounding the boron atom, making it sp2 hybridized. Anything that is sp2 hybridized will have a trigonal planar electron domain geometry. An example of an atom being sp3 hybridized would be the carbon in methane. Anything that is sp3 hybridized will have a tetrahedral electron domain geometry. Atoms that have 5 electron domains are sp3d hybridized, thus having a trigonal bipyramidal electron domain geometry. Lastly, atoms with 6 electron domains are sp3d2 hybridized, making it exhibit an octahedral electron domain geometry. Now, due to the nature of lone pair atoms, the shape of a molecule can be changed despite having the same number of atoms to other molecules. This is because lone pair electrons cannot draw an electron cloud towards it due to the absence of an atomic nucleus at its far end, making the charge within the said orbital to be concentrated closer to the central atom. As a result, the lone pair atoms will push the bonding orbitals closer together. An example of this can be seen in a water molecule, as the effects of lone pair atoms changes its appearance, causing the geometry to look bent. To sum it up, the number of electron domains that surround an atom, whether that be covalent bonds or lone electron pairs, determine the hybridization of the central atom. The hybridization should contain as many letters as there are electron domains. The hybridization correlates with a particular electron domain geometry, and with each electron domain geometry, there can be multiple geometries as we replace bonds with lone electron pairs.
Thank you, Mr. Girl. Now, I am Gloriesta and I will be talking about polarity of simple molecules. Now, what comes to our mind when we hear the word polarity? According to ChemLibratex.org, polarity is a physical property of compounds that relates to other physical properties such as melting and boiling points, solubility, and intermolecular interactions between molecules. For the most part, there is a direct correlation between the polarity of a molecule and the number and types of polar or non-polar covalent bonds which are present. In a few cases, a molecule may have polar bonds but in a symmetrical arrangement, which then gives rise to a non-polar molecule such as carbon dioxide. In other definitions, polarity may also mean the distribution of electric charge over the atoms joined by the bond, or polar molecules are those that possess regions of positive and negative charge. Polar molecules occur when 2 atoms do not share electrons equally in a covalent bond. A dipole forms with part of the molecule carrying a slight positive charge and the other part carrying a slight negative charge. This happens when there is a difference between the electronegativity values of each atom. An extreme difference forms an ionic bond, while a less than difference forms a polar covalent bond. Fortunately, you can look up electronegativity on table to predict whether or not atoms are likely to form polar covalent bonds. If the electronegativity between the 2 atoms is between 0.5 and 2.0, the atom forms a polar covalent bond. If the electronegativity difference between the atoms is greater than 2.0, the bond is ionic. Ionic compounds are extremely polar molecules. There are 3 main properties of chemical bonds that must be considered, namely their strength, length, and polarity. The polarity of a bond is the distribution of electrical charge over the atoms joined by the bond. Specifically, it is found that while bonds between identical atoms, as in H2, are electrical uniform in the sense that both hydrogen atoms are electrical neutral, both bonds between atoms of different elements are electrically inequivalent. In hydrogen chloride, for example, the hydrogen atom is slightly positive charge, whereas the chlorine atom is slightly negative charge. The slight electrical charges on the similar atoms are called partial charges, and the presence of partial charges signifies the occurrence of polar bond. This image shows the comparison of ionic, polar, and non-polar bonding. We can see that in ionic, it is a complete transfer of electrons, full ionic charges, and it has both metal and non-metal. While in the covalent bond, there are two types, mainly polar and non-polar. In polar, it is the unequal sharing of electrons, while in non-polar, it is the equal sharing of electrons. While the polar has partial ionic charges, non-polar has no charges. The difference between the polar and non-polar bonding is that polar has two different nonmetals, while non-polar has two identical nonmetals. Now, let's talk about polarity dipole. In polarity dipole, polarity results from the uneven partial charge distribution between various atoms in a compound. Atoms such as nitrogen, oxygen, and halogens that are more electronegative have a tendency to have partial negative charges. Atoms such as carbon and hydrogen have a tendency to be more neutral or have positive charges. Electrons in a polar covalent bond are unequally shared between the two bonded atoms, which results in a partial positive and negative charges. The separation of the partial charges creates a dipole. The word dipole means two poles, the separated partial positive and negative charges. A polar molecule results when a molecule contains polar bonds in an unsymmetrical arrangement. The polarity of a bond arises from the relative electron negativities of the elements. Electron negativity, it will be recalled, is the power of an atom of an element to attract electrons toward itself when it is part of a compound. Thus, although a bond in a compound may consist of a shared pair of electrons, the atom of the more electronegative element will draw the shared pair toward itself and thereby acquire a partial negative charge. The atom that has lost its equal share in the bonding electron pair acquires a partial positive charge because its nuclear charge is no longer fully cancelled by its electrons. Polar molecules include water, ammonia, sulfur dioxide, hydrogen sulfide, and ethanol. Note that ionic compounds such as sodium chloride are polar. However, most of the time when people talk about polar molecules, they mean polar covalent molecules, and not all types of compounds with polarity. When referring to compound polarity, it is best to avoid confusion and call them non-polar, polar covalent, and ionic. Polar molecules are those that possess regions of positive and negative charge. Water is an example of a polar material. The type of bond it has when coupled with its shape gives one end of the molecule a slightly positive charge, or as we call the hydrogen end, and the other a slightly negative charge, the oxygen end. These charges are attracted to the charges on other polar molecules. Generally, molecules with oxygen atoms, nitrogen atoms, or ionizable groups tend to be polar. On the other hand, non-polar molecules are those that do not possess regions of positive and negative charge. Ethane is an example of a non-polar material. The type of bond it has when coupled with its shape leaves the molecule with no regions of charge. Generally, the more carbon and hydrogen atoms a molecule has, the less polar or more non-polar it will be. Non-polar molecules is when molecules share electrons equally in a covalent bond, but there is no net electrical charge across the molecule. In a non-polar covalent bond, the electrons are evenly distributed. You can predict non-polar molecules will form when atoms have the same or similar electronegativity. In general, if the electronegativity difference between the two atoms is less than 0.5, the bond is considered non-polar, even though the only truly non-polar molecules are those formed with identical atoms. Non-polar molecules also form when atoms share a polar bond arrangement such that the electrical charges cancel each other out. Non-polar molecules are of two types. Molecules whose atoms have equal or nearly equal electronegativities have zero or very small dipole moments. The second type of non-polar molecule has polar bonds, but the molecular geometry is symmetrical, allowing the bond dipoles to cancel each other out. Examples of non-polar molecules include any of the noble gases, any of the homonuclear diatomic elements, carbon dioxide, benzene, carbon tetrachloride, methane, ethylene, hydrocarbon liquids such as gasoline and toluene, and most organic molecules. If you know the polarity of molecules, you can predict whether or not they will mix together to form chemical solutions. The general rule is that like dissolves likes, which means polar molecules will dissolve into other polar liquids and nonpolar molecules will dissolve into nonpolar liquids. This is why oil and water don't mix. Oil is nonpolar while water is polar. It is helpful to know which compounds are intermediate between polar and nonpolar because you can use them as an intermediate to dissolve a chemical into one it wouldn't mix with otherwise. For example, if you want to mix an ionic compound or polar compound in an organic solvent, you may be able to dissolve it in ethanol, polar but not by a lot. Then you can dissolve the ethanol solution into an organic solvent, such as xylene. We can find the polarity of a molecule by determining the electronegativity of the atoms in the molecule and determining the shape or geometry of the molecule. As we wrote, electronegativity is a tendency of an atom to attract a bonding pair of electrons. These are the electronegativity difference. Greater than 1.8 is ionic bond, less than 1.7 is considered covalent bond or electrons are shared. Greater than 0.5 is polar covalent bond, while less than 0.5 is nonpolar covalent bond. These are the key takeaways of polar and nonpolar. In chemistry, polarity refers to the distribution of electric charge around atoms, chemical groups, or molecules. Polar molecules occur when there is an electronegativity difference between the bonded atoms. Nonpolar molecules occur when electrons are shared equally between atoms of another atomic molecule or when polar bonds in a larger molecule cancel each other out. If the bond is polar, then the molecule can either be polar or nonpolar. However, if the bond is nonpolar, then the molecule is automatically nonpolar.
My name is Justa. My name is Justin Jolniza, and now I will be discussing functional groups and organic compounds. Functional groups, according to Hellenstein, PhD 2020, functional groups are collections of atoms in organic chemistry molecules that contribute to the chemical characteristics of the molecule and participate in predictable reaction. These groups of atoms contain oxygen and nitrogen or sometimes sulfur attached to the hydrocarbon skeleton. Organic chemists can tell a lot about a molecule by the functional groups that make up a molecule. In organic chemistry, a functional group is a set of atoms within molecules that function together to react in predictable ways. Functional groups undergo the same chemical reactions no matter how large or small the molecule is. When these groups are attached to molecules, they convert the molecule into either complexions or polyatomic ions. Examples of functional groups include the hydroxyl group, ketone group, amine group, and ether group, and other groups that will be discussed later on. Based on the functional groups they contain, organic compounds are divided into several broad categories. Positions of functional groups in the fundamental hydrocarbon framework are indicated by numbers in the systematic names of organic compounds. In organic chemistry, there are 9 common functional groups. All common groups are named with accordance with IUPAC, or the International Union of Pure and Applied Chemistry Nomenclature Guidelines, and the priority order of functional groups in IUPAC nomenclature. Aldehyde, amine, hydroxyl, ketone, phenyl, amino, ether, amide, and ester are some of the most prevalent functional groups in organic chemistry. Additionally, a brief description of the constitution of each of these groups is also provided. Number 1 is hydrocarbons. Alkanes, alkenes, alkynes, and sometimes the derivatives of benzene are represented by the symbol R. These groups are also referred to as hydrocarbon groups since they contain only carbon and hydrogen atoms. However, they may vary in types of bonds between 2 carbon atoms, such as double or triple bonds. The reactivity of these groups varies due to the nature of the carbon-carbon bond. Some groups are made up of a long-branched alkane or a ring-structured alkane, which are assigned specific names. Examples include names such as bornyl and cyclohexyl. A few functional groups, including carbon, are illustrated as shown in Figure 4.1. Haloalkanes, or alkyl halides, are the functional groups which contain a bond between a carbon atom and a halogen. The prefix used to denote the halogen is halo. For example, the compound CH3F can be called fluoromethane, and the prefix here is fluoro. The suffix used to denote the halogen is the halide. For example, the same compound fluoromethane can also be referred to as methyl fluoride, the suffix being fluoride. Number 3 is oxygen-containing functional groups. The properties of the functional groups containing a carbon-oxygen bond are entirely dependent on the hybridization of carbon-oxygen bond. This can be explained by the electron-dating effect of the sp3 hybridization of oxygen, which can be observed in alcohols, in sharp contrast with the electron withdrawing effect of the sp2 hybridized oxygen, which can be observed in the carbonyl groups, which contain a carbon-oxygen double bond. Functional groups are atomic clusters within molecules that have their own distinct properties, regardless of the other atoms in the molecule. Alcohols, amines, carboxylic acids, ketones, and ethers are all examples of organic compounds. In a standard organic chemistry course, there are around 14 main functional groups, with another set of 8 showing up from time to time. Alkenes and alkynes are hydrocarbon functional groups. The pi bond in multiple bonds accounts for the reactivity of alkenes and alkynes. Benzene rings are a special type of hydrocarbon, historically because of the special aroma, sweet smelling, that benzene and its derivatives release. They are called aromatic compounds. The structure of benzene can be represented as 3 carbon double bonds alternate with single bonds. However, the actual structure of benzene has nothing to do with the alkenes. Amine is the organic derivative of ammonia. When the hydrogen atoms in NH3 is replaced with R groups, it produces amine. The amine can be primary, secondary, or tertiary depending on how many R groups are connected with nitrogen. The amines can also be named with common names. The hydroxyl group is an oxygen atom bonded to a hydrogen atom. Hydroxy groups link biological molecules together via dehydration reactions. In organic chemistry, the term alcohol refers to a compound containing the hydroxy group. Depending on the position of the OH group, alcohols can be categorized as primary, secondary, or tertiary. Another functional group that contains the oxygen atom in single bonds is ether. In ether, the oxygen atom connects with 2 carbon-containing R groups through 2 carbon oxide bonds. For compounds with ether as the only functional group, it is usually named with the common name alkyl-alkyl ether. When the 2 alkyl groups are the same, they can be combined as dialkyl. The thiol functional group is similar to the hydroxyl group, except the oxygen atom in the hydroxyl group is a sulfur atom in the thiol group. The thiol functional group is also known as sulfhydryl functional group. Molecules that contain thiol groups are also called mercaptans. Ketone is a carbon atom double bonded to an oxygen atom that appears as a bridge between 2 other parts of a molecule. Other name for this group is the carbonyl functional group. Note how the aldehyde is a ketone, where 1 R is the hydrogen atom. The last 4 functional groups are related in terms of structures and chemical properties. When an OH group is connected with carbonyl, the whole COOH is called carboxylic acid functional group. The other 3, ester, aldehyde, and amide, are all derivatives of carboxylic acid, meaning they can be prepared with carboxylic acid as a starting material. For these 3 functional groups, it is important to remember that the W part has to be considered together with the carbonyl, and overall, it determines the functional group correctly. For example, the COOR is ester. It cannot be recognized as ketone, plus, and ether. And there's a group of about 8 functional groups that you'll see a little but less often, but they still have their place. Consists of nitrile, epoxide, disulfide, amine, acid chloride, anhydride, nitro, and sulfide. The 8 functional groups are the following.
Thank you so much, Ms. Lanuza. Once again, I am Andrea Milici-Licup, and I will be explaining structural isomerism. But before going there, let me first explain isomerism. Isomerism is a phenomenon in which more than one compound has the same molecular formula but differs in their chemical structures. When isomerism is a phenomenon, isomers, on the other hand, are the actual compounds. Isomers are the compounds with the same molecular formula but different chemical structures. So, they have different structural formulas and/or spatial arrangements. The term isomer came from the Greek words isos and meros, which means equal and parts, respectively. So, we can use the origin of this word to remember the meaning of isomers. Since isomers have the same chemical formula, it means that they have the same number of elements, and therefore, they have equal parts. The only difference is that their parts are arranged differently in their chemical structures. In 1830, this term was coined by the Swedish chemist Jacob Berzelius. There are 2 main classes of isomers. First, we have constitutional or structural isomers, and second, we have stereoisomers. Constitutional or structural isomers are isomers that have the same molecular formula but different structural formulas. They differ in the way their atoms are connected. Here is an example. We have the molecular formula C5H12. We can see that although butane and isobutane have the same molecular formula, they differ in the way their atoms are connected. We can observe that in butane, the carbon atoms are arranged in a linear way, while in isobutane, we can see that CH3 or methyl, is connected on the second carbon atom. Since they have the same molecular formula but different structural formulas, they are structural isomers. Second, stereoisomers are isomers that have the same molecular and structural formula but different spatial arrangements. So, they are connected in the same way but differ in the way their atoms are arranged in space. Here are examples. We can see in each pair that they have the same molecular formula and are connected in the same way, however, they have different spatial arrangements. Also, in structural isomers, the properties of the molecules are different from each other, while in stereoisomers, the properties of the molecules are mainly similar. Here in structural isomers, chirality is absent, while chirality is present in stereoisomers. There are two kinds of stereoisomers. First, we have conformational isomers. These are also called conformers. These are stereoisomers that rapidly interconvert at room temperature, and thus, they cannot be separated. Additionally, there are two kinds of conformational isomers. First, we have those due to rotation about carbon-carbon single bonds, and then we have those due to amine inversion. Second, we have configurational isomers. These are stereoisomers that cannot interconvert unless covalent bonds are broken. Because configurational isomers cannot interconvert, they can be separated. In addition, there are two kinds of configurational isomers. We have cis-trans isomers and isomers that contain asymmetric centers. Now, I'll explain the three kinds of structural isomerism. First, we have chain isomerism. It is also known as skeletal isomerism. It occurs when two or more compounds with the same molecular formula have different main chains. Take note of the word chains. In here, there is a difference in the atomic arrangement of the carbon in the carbon chain of a molecule. Here is an example. Although N-butane and isobutane have the same molecular formula, which is C5H12, their carbon atoms or carbon chains are arranged differently. Because of this, they are considered as chain isomers. Second, we have position isomerism. It occurs when the position of the functional group with respect to the main chain atom changes due to the unsaturation occurring in the chain. So in here, the functional group is attached to the main chain in a different location. So take note about the positions of the functional group. Here is an example. We have the molecular formula C3H7Br. So in one bromopropane, the bromine, the halogen bromine, is connected on the first carbon atom, while in 2-bromopropane, the halogen bromine is connected on the second carbon atom. Since the functional groups are in different locations in both compounds, they are position isomers. And third, we have functional group isomerism. It occurs when molecules that have the same molecular formula are reorganized to give a different functional group. So in here, compounds with the same elements, when organized differently, produce a different functional group. Take note of the word functional group. For the examples, here are 4 different types of functional groups pairs that one should know in A-level chemistry according to the chemistry teacher. First, we have C4H8. We can see that 1-butene is an alkene, and when reorganized, it can produce cyclobutane, which is a cycloalkane. Second, we have C3H6O, which can produce the functional group isomers aldehyde and ketone. Third is C3H8O, which can produce alcohol, and when reorganized, can produce ethene. And lastly, we have the molecular formula C2H4O2, which can produce the isomers carboxylic acid and an ester. This is the end of my part of the discussion, and now here is Mr. Luke Buncha.
Thank you, Ms. Lico. Again, I am Luxi Buncha, and in this section, I will discuss the formation and structure of polymers. Without further ado, let's start. Polymers are defined as any class of natural or synthetic substances composed of relatively large molecules named macromolecules. which are composed of multiple smaller chemical units called monomers. They make up many materials that make up living organisms, minerals, and man-made materials, such as but not limited to cellulose, proteins, nucleic acid, diamond, quartz, feldspar, concrete, glass, paper, plastics, etc., according to Britannica and D. To clarify, the word polymer means that there is not a specific number of monomer units. However, when the amount of monomers is large enough, the compound is often called a high polymer. Next, let's classify polymers based on their source. First are natural polymers. They occur naturally in live organisms such as plants and animals. Examples are starch, cellulose, and rubber, according to Bijus and D. Next are semisynthetic polymers. They are made from natural occurring polymers that undergoes further chemical modification. Examples are cellulose nitrate or cellulose acetate. Finally, we have synthetic polymers. They are man-made polymers, and the most known example of them are plastics. Following slides, we will talk about the basic polymer structures, namely linear polymers, branch polymers, network polymers, and cross-linked polymers. So let's start. Linear polymers are repeating units that are joined together to form a single flexible chain. These polymeric chains are bonded by physical attractions. They have extensive van der Waals attractions to keep the chains together. Since linear polymers are easily breakable by heat, they are usually thermoplastic. The heat causes the bonds between the long chains to break, allowing the chains to simply pass each other, allowing the material to be remolded. Upon cooling, the bonds between the long chains reform, causing the polymer to harden, according to Matsi 81 and D. As we can see in this illustration of a linear polymer, there is a series of repeating monomers that form the entirety of its structure. Next are branch polymers. Branch polymers resemble linear polymers with the addition of shorter side chains hanging from the main chain like a backbone. Monomers with two or more end groups commonly support branching. For a polymer to be considered as a branch polymer, the side chains should consist of one complete monomer unit. Due to the presence of the shorter chains, the efficient packaging of the polymers is interfered, causing it to be less dense when compared to linear polymers. The length of the branches vary from long or short branches. Similar to linear polymers, branch polymers are typically thermoplastic due to the short chains not bridging from one longer backbone to another, causing heat to break the bonds between the branch chains. According again to Matsi 81 and D, there are a few very complex branch polymers that resists that melting, causing it to break up before softening, meaning a very few branch polymers are thermosets. And guys, as we can see from the illustrations of these several branch polymers, although they have varying lengths of their protrusions or their side chains, what's common with all of them are at least each and every one of these have one complete monomer unit, as mentioned earlier. So let's move on. Next are cross-linked polymers. They are polymers in which the adjacent polymers are connected in a three-dimensional network structure. Since the chains link from one backbone to another, they are held by stronger covalent bonding compared to the weaker van der Waals forces. The covalent bonding makes most cross-links polymers thermoset, with a few exceptions. So you can see here, there are cross-links between three polymers, unlike branch polymers and linear polymers, which only have protrusions or are standalone. Finally, we have network polymers. These are the most complex polymers when compared to its other structure counterparts. They are heavily linked to form a complicated network of three-dimensional linkage. Those polymers are nearly impossible to soften when heating without it degrading the underlying polymer structure, meaning they are thermosets. As we can see here in the last part, there are many connections between several polymers. This alone makes it a much more complex polymer when compared to linear polymers, branch polymers, or cross-linked polymers. In the final part of this presentation, I will talk about polymerization. Polymerization is the process in which polymers are formed from small molecules called monomers. It is categorized into two classes, the addition polymerization and the condensation polymerization. First, let's discuss the process of addition polymerization. Addition polymerization is also called chain rule polymerization, and it requires the presence of an initiator or a compound that will react with the monomer to form a reactive compound, which would start the linking process or the propagation of the polymer. The addition of each monomer unit increases the overall length of the polymer. So in order to understand the process of polymerization, let's look at how polyethylene is formed. First, let's understand what the curly arrow notation means. Curly arrow notation is a way in indicating where electrons are moving. They are indicated using arrows. Two barbed arrows show the movement of two electrons, and a single barbed arrow shows the movement of one electron. In this example, only a single barbed arrow will be used. As we can see in this picture, it is shown the difference between a single barbed arrow and a two barbed arrow. The process of addition polymerization is divided into three phases: the initiation phase, the propagation phase, and the termination phase. The process starts with the initiation phase where the initiators, such as peroxide, break down to an unstable compound called a radical. The radical is a reactive compound with an unpaired electron and is given the generic notation R. In this phase, the initiator is added to the monomer, where it forms a new radical. In this case, it's the unpaired electron on a carbon atom. What happens in this illustration is one electron from the double bond will combine with an electron from the radical to form a bond between the radical and the carbon. And in the process, a new radical is formed, which is the carbon atom. The next phase is the propagation phase. In this phase, as more ethylene monomers are added, the radical on the equation, in this case the carbon, would form a bond with the ethylene monomers added, forming a bond with the added ethylene as well as forming a new radical, in this case again, the carbon from the added monomer. This process will repeat itself until it reaches the termination phase. The termination phase is where the radical transference ends, and one of the ways this could happen is when a radical from a chain meets another radical from the initiation phase as shown below. Now what we have left is a stable molecule that won't be reactive anymore. Anyway, always take note that the bonds of the monomer is written facing up and down rather than at angles, and lines should be written at the left and right of each monomer unit indicating that it reacts with the other ethylene units. The N on the outside of the parenthesis, on the other hand, indicates how many monomers are repeated in the reaction, or in the formation of the polymer. The other type of polymerization that we will discuss in this video is the condensation polymerization. It is a subtype of step growth polymerization where monomers react with each other while releasing byproducts such as water or methanol molecules. Let's take a look at the process of condensation polymerization, to be exact, the process of how polyesters are formed. Polyesters has a common combination of two monomers, a dicarboxylic monomer with two carboxylic groups, and a diol monomer with two alcohol groups. These rectangles represent the rest of the molecule, and we use that in general examples to not make the problem more complicated. In order for these two different monomers to combine, the dicarboxylic acid must give up the OH group, and the diol must give up a hydrogen atom to form a water molecule. In this case, the dicarboxylic acid and the diol will combine. However, in order to make this a repeating unit, the OH group and the hydrogen molecule from the outer part of the combined monomers will become a water molecule. So in every repeat unit, two water molecules are formed. As we can see in this example, the HO group or the OH group from the left side of the equation and the hydrogen group from the OH group from the right side of the equation combine to form a water molecule. To finish, we add the brackets on either ends and an N to indicate that the dimer is repeated N times. This is an ester link, hence the name polyester. In order for a condensation polymerization to occur, we must fulfill three conditions. First, each of the monomers has to have at least two functional groups. As we can see, the dicarboxylic acid has two carboxylic groups and the diol has two alcohol groups. Second, there needs to be two different functional groups overall, again, carboxylic acid and alcohol. And third, a molecule is given off. Commonly, this is water.
The following terms were used in our presentation.
Here are the references used in our presentation.
Once again, I am Kurt Russell.
And I am Loxi Buncha. We hope that our video discussion about organic compounds and its subtopics has been of benefit and brought new knowledge and insights to everyone. Thank you for listening!